Today we'll be dealing with the concept of random variables. And the first thing we need to understand is the definition that is attached to random variable. Now, what is random variable? Now, a random variable can be defined as a variable whose outcome cannot be predetermined with precision, which outcome cannot be ascertained with precision. So any of such variable is referred to as a random variable. So another word for the word random is called stochastic. That is to say that I cannot predetermine the outcome of a given variable, an experiment, then that experiment is being tagged a random experiment, or perhaps an experiment with a random. Now, like I said, that a random experiment can either be discrete or continuous. Now, for discrete, you can it's actually countable. It's whole in nature. So that is why it's referred to as what? As discrete. But continuous. For instance, let's give an instance of the fact that a boss comes to pick up a child early in the morning for school. Then the mother of the boy discovered that the bus driver comes between 8 a.m. in the morning and 8:05 a.m. in the morning. The woman discovered by experiment that this happens daily. Then the time by which this man is going to come is continuous. It's not discrete in a sense because time is not discrete. Time is continuous. So we have examples of variables that are continuous, examples of variables that are discrete. For instance, if I was to ask you how many of you, or what's your family size, you are going to be giving me a discrete value, say 7, 8, 10, 3, what have you. That means variables from the set of natural numbers. Not will you ever tell me that 2.5 or 2.2, it doesn't make too much sense for you to say that your family size is 2.2 because the wife is pregnant. No. So, but when it comes to continuous distribution, we discuss the concept of continuity. For instance, we talk about your height, we talk about the breadth, any dimension, we talk about time. These are continuous variables. Now, in statistics, we have discovered that some particular distribution follow a definite pattern. And that is why, like I said, it's being grouped into discrete and continuous. So in discrete distribution, or in discrete probability distribution, we have the concept of Bernoulli, we have binomial, we have hypergeometry, we have the uniform, we have the multinomial, we have the Pascal distribution or the geometric distributions and the likes of them, even the Poisson as well. And the continuous as well, you have your beta distribution, you have your gamma distribution, you have your normal distribution, you have your uniform distribution, and what have you as well. But in this class, we'll first of all be focusing on the discrete distribution. And we'll start off with what we call the Bernoulli distribution, the mother of all distribution, or perhaps all discrete distribution. Like I said, that the Bernoulli is the mother of all distribution, like statistician will have it, but to be precise, we say it's the mother of all discrete distribution. And just like any other probability, that is what Bernoulli is. It has its own PDF, its own PMF, I mean to say, the probability mass function, and it has its own assumptions that needed to be fulfilled, that needs to be fulfilled before you can detect or denote such a distribution as Bernoulli. Now, what is Bernoulli distribution? Now, a Bernoulli distribution is a distribution with a single trial but two outcomes. So the moment you run an experiment just once, and the outcome is can be grouped into two, either true or false, up or down, any two outcomes, then we refer to such an experiment as what? As Bernoulli. So it's just an experiment, like I said, that happens in one trial, and it has its own PDF to be of the form, say, P of x equals to x equals to something of this form. You could make use of P or Q or theta, it doesn't matter. But okay, for the sake of this class, let me just make use of P so that I will not need to put in P raised to power x, open the bracket, 1 minus P raised to power what? 1 minus x. Now such is what? Such is the distribution of Bernoulli. Is 0 s where? with x ranging between 0 and 1. That is the outcome. That is the PDF of a Bernoulli distribution. Now, you can also actually in some textbooks you can see them as theta raised to power x 1 minus theta raised to power 1 minus x is 0 elsewhere. Now, what does this mean? This is a piecewise function indicating the PDF of a Bernoulli, and 0 elsewhere implies that is if the experiment never occurred at all, then you have something called a 0. I said earlier on that the outcomes of Bernoulli had been distributed into two cadres, and the cadres are both success and failure, where we denote our P as what? As success, and our what? And the Q as failure. Now, the success in this context does not actually mean the success, neither does the Q in this context does not actually mean the failure. The success implies that it happened or it came to pass, while the failure implies it did not happen or it did not actually come to pass. That is what the Q implies, not the success like having cars or whatever, what have you. So if we were to solve for the mean, because like I said, it's a probability mass function, you still follow the concept of the fact that don't forget your axioms of statistics, your axioms of probability, which states that your P plus Q must add up to become 1, just like what? The summation of all of your probability, all of your probability distribution must actually earn you 1 equally. These are probabilistic axioms. They are called probabilistic axioms actually. That's what I have to. Such also is the attribute of a Bernoulli distribution. Such also is the attribute of a Bernoulli distribution. A legitimate probability function must always add up to become 1. No matter what the probability function may look like, it must always add up to become 1. That is one of the beautiful attributes of a probability distribution. And you can as well solve for the mean and the variance, even the truthness and the kurtosis of any distribution. But for the sake of this class, we are going to be looking at, we are going to be proving that Bernoulli is legitimate probability function, and we are also going to be looking at the concept of the fact that we can solve for the mean and the variance of a Bernoulli distribution. Now, to prove that Bernoulli is a legitimate probability mass function, then we are going to be having this done. That to prove that, we have that the probability of what? Of x equals to x, like I told you initially, of a Bernoulli distribution is the summation of all of the what? All of the outcomes, which is 0 and 1, that I have it to be, if you have not forgotten, I ranging from 0 down to 1, basically. I'm going to be having it to be my probability function of theta raised to power x of 1 minus theta raised to power 1 minus x. So what do I do? What I do is that, don't forget that this implies our summation, which means plus. I'm going to be splitting this up so that it becomes what? It becomes theta raised to power x and in bracket 1 minus theta raised to power 1 minus x. This is for when x is actually equals to 0, plus theta raised to power x of 1 minus theta raised to power 1 minus x. This is when x is actually equals to 1. So I try to fix this up, and I'll be having it to be that what? To be when it is 0, theta raised to power 0, 1 minus 0, 1 minus theta, I mean to say 1 minus 0, plus theta raised to power 1, 1 minus theta, then 1 minus 1. So I'll be having this to be anything raised to power 0 is still 1. Then here is 1 minus theta plus theta, 1 minus theta raised to power 0, which will actually fetch us 1. So by expansion, I have this to be 1 minus theta plus theta times 1, which will give me minus theta plus theta will give me 0. So I have it to be 1. Hence, we have just proven that a Bernoulli distribution is a legitimate probability function. Then, to solve for the mean of Bernoulli, it goes down to solve for the mean of Bernoulli distribution, or the mathematical expectation of a Bernoulli distribution. We need to go to the corridor of expectation, the mathematical expression of saying that E of x of Bernoulli equals to the what? To the summation of x of what? Of P of xi. This is how to solve for the expectation of of Bernoulli ranging from 0 down to 1. Then what do I have next is that since I know that my x is actually ranging between 0 and 1, I'm going to be writing it as the mathematical expectation of a Bernoulli distribution to find the mean is the summation still of what? Of I ranging from 0 down to 1 of xi of the probability distribution of Bernoulli given as t tan raised to the power of x and 1 minus t tan raised to the power of x minus 1 minus what? 1 minus x. So from there you do your simple expansion of saying that first of all I have a 0, t tan raised to the power what is 0, 1 minus t tan raised to the power what 1 minus 0, then plus 1 followed by 1, t tan raised to the power 1 or 1 minus t tan raised to the power 1 minus 1. So I'm going to be having this 0 times all of this will actually give me 0. Then this will fetch me t tan raised to the power 1 is t tan times 1 minus t tan raised to the power 0, which will give me t tan times 1, and that is t tan. So don't forget that I said that your t tan simply typifies your p, which is your probability of success. So therefore, the mathematical expectation of a Bernoulli distribution is given as p. But to solve for the variance, to easily recall that our variance value, the variance value of a Bernoulli distribution, random variable, is given as what? The mathematical expectation of the square of the random variable of a Bernoulli distribution minus the mathematical expectation of a Bernoulli distribution all in what? All in square. We already decoded this. We already know what the value of e of x is, which is just p. But there's a need for us to find what the value of ex squared is. So we are going to be looking for, first of all, the value of ex squared, which we know will give us the summation still of x squared of p of what? P of x of a Bernoulli what distribution, value ranging from a 0 down to 1. So what else am I to do is that I'm going to replace my p of x value with a Bernoulli distribution of, say that the summation of I ranging from a 0 down to 1 of x squared of t tan raised to the power what? Raised to the power x of 1 minus what? 1 minus t tan raised to the power 1 minus x. So you do your simple expansion like we did initially, so that we will be having something of the form, say, is 0 squared, then t tan raised to the power 0 of 1 minus t tan raised to the power 1 minus what? 1 minus 0, then plus 1 squared of t tan raised to the power 1 of 1 minus t tan raised to the power what? Raised to the power 1 minus 1. You know that this automatically becomes 0 because it's multiplied by 0. Then we know that this will become 1 times t tan times 1, because anything raised to the power 0 will actually give us 1. So our our expectation of the random variable of a Bernoulli squared will give us t times 2. And don't forget that I told you that our t tan also typifies our p, probability of success. Then in other words, we have to return this back to our equation of saying that our variance of what? Of x is then equals to theta, since our expectation of x squared gives us theta. Then minus t tan squared. Why? T tan squared because our expectation of our mathematical expectation of a Bernoulli distribution was given to be t tan as well, but it's a squared outside. So when I factorize t tan, I'm going to be having 1 minus t tan, which at the end is going to be giving me what? Is going to simply be giving me that the variance of what? Of x is simply, my t tan means p, and 1 minus t tan means 1 minus p, which means pq. So in summary, we can simply say that the expectation, which is the mean of my Bernoulli, is p, and the variance of my Bernoulli distribution is pq. So with this, we have just done well, I've done fine. So please do ensure you subscribe to this channel so you can get notification when we post a new video. And as well, please drop a comment at the comment section so we can know if you have questions.